The radar operator felt his fingers shake as he stared at the glowing screen. It was October 1977, and Senior Lieutenant Mail Baranov had spent years monitoring Soviet airspace from his post near Minsk. Thousands of aircraft had crossed the scope over the decades. He knew their signatures instinctively: the wide, lazy echo of heavy transports, the sharp, precise return of a MiG-25 interceptor, even the faint, almost ghost-like trace of high-altitude reconnaissance aircraft skirting the border. This contact defied everything he knew. At 3:47 hours, a return appeared roughly 40 kilometers to the west. The signal was ordinary at first, consistent with conventional aircraft. Altitude was estimated at 8,000 meters. The flight path resembled a standard NATO patrol. Baranov recorded the data, lifted his tea to his lips, then looked back at the scope. The contact was gone. It hadn't drifted away or weakened gradually. It had vanished instantly, as if erased. Baranov checked his instruments. All systems reported normal operation. He blinked, rubbed his eyes, and continued watching. 3 minutes later, the return reappeared. Same bearing, same altitude, but now the radar cross-section was absurdly small, no larger than that of a sizable bird, despite speed and movement consistent with a tactical jet. Baranov immediately contacted his supervisor, Captain Oleg Dmitriev, a veteran with 15 years of experience tracking Western aircraft. Dmitriev stood behind Baranov as they watched the contact flicker unpredictably over the next 20 minutes, appearing, disappearing, then returning at wildly inconsistent strengths. When it vanished for the last time, Dmitriev lifted the secure phone and called Moscow. Within 6 hours, specialists from the Soviet Air Defense Forces arrived carrying portable spectrum analyzers and backup radar units. They confirmed what Baranov already knew. The radar station was functioning flawlessly. The upgraded P-18 spoon rest system, capable of detecting large bombers at distances of up to 300 kilometers, showed no mechanical or electronic faults. Yet the recorded data revealed something deeply unsettling. The target's radar return fluctuated by factors of thousands, strong enough at one moment to resemble a fighter aircraft, then dropping to barely above background noise seconds later. There was no change in range, altitude, or aspect angle that could account for such behavior. The engineers understood radar physics. Conventional aircraft reflect radio waves in predictable ways determined by size, shape, and materials. Metal surfaces produce strong echoes. Curved structures scatter energy according to well-understood equations. Radar cross-sections vary during turns or maneuvers, but always within known mathematical limits. An F-15 Eagle presents roughly 25 square meters of radar cross-section head-on. A B-52 bomber exceeds 100 square meters. Even the State Route 71 Blackbird, designed to minimize detectability through altitude and speed, still returns about 1 square meter. This object behaved as though electromagnetic laws no longer applied. At one instant, it appeared solid and unmistakably present. At the next, radar energy passed through empty sky. The technical report submitted in Moscow 3 days later used cautious, bureaucratic language, but its implication was unmistakable. The Americans had achieved what Soviet physicists believed to be impossible: an aircraft capable of controlling its own visibility. What Soviet intelligence did not yet realize was that this radar ghost carried the designation AvBlue, and that it was built using mathematical principles first published in Moscow 15 years earlier. At the time, Soviet engineers had dismissed the work as elegant theory with no practical application to aircraft design. Across the Iron Curtain, NATO radar stations operated under different procedures, but confusion was the same. At Ramstein Air Base in West Germany, Technical Sergeant James Morrison had clearance for classified tracking operations. He had monitored U-2 flights, State Route 71 reconnaissance missions, and experimental electronic warfare tests. He understood secrecy. So when a range controller announced a special test window for November 16, 1977, Morrison assumed it would be another evaluation of experimental radar-absorbing materials. He was wrong. The initial data looked ordinary, exactly what Morrison expected. Procedure was standard. At precisely 14:20 hours, a radar contact appeared on schedule, entering from restricted airspace over the North Sea. Morrison's APQ-120 radar, a high-precision system built to vector interceptors onto hostile targets, displayed a return consistent with a single-engine fighter. Range, 60 kilometers. Altitude, 6,000 meters. Speed, 400 knots. He confirmed the track, logged the parameters, and prepared to observe the planned test sequence. Then the aircraft began its inbound run toward the calibration zone. Without warning, the radar cross-section dropped sharply. Morrison watched the numerical readout plunge from 15 square meters to just 2 in a single sweep. He dismissed it as a momentary anomaly, either a sense of fluctuation or a software hiccup. The next sweep showed 0.3 square meters. That was impossible. He was tracking a jet aircraft, not birds or atmospheric clutter. As the target passed directly overhead at 4,000 meters, the radar struggled to maintain a stable lock. The cross-section oscillated wildly between 0.1 and 0.21 square meters, smaller than a return from Sparrow. Morrison trusted this system. He had calibrated it countless times using known references. A Cessna 172 consistently produced a 1 square meter return. The AGM-86 cruise missile, purpose-built for low observability, registered around 0.1 square meters. Yet here was an aircraft with wings, a jet engine, and a metal airframe, producing a signature that should not exist outside specialized stealth missile programs. He ran a full diagnostic check. Every subsystem reported normal performance. No faults. No errors. The radar wasn't lying. The aircraft simply wasn't visible in any conventional electromagnetic sense. The test sequence continued for 40 minutes. The unknown aircraft flew straight-line passes, steep banking turns, and simulated attack profiles. Throughout the run, Morrison's radar alternated unpredictably between clean, solid tracks and total loss of contact. During one especially aggressive maneuver, the aircraft turned directly toward the station, presenting what should have been the largest possible frontal radar return. The display showed 0.08 square meters. Morrison did the math instinctively. ANF-4 Phantom presented approximately 6 square meters head-on. This contact was nearly 750 times smaller, despite being close enough that the roar of its engines could be heard through the concrete walls of the radar facility. Once the aircraft had cleared the range, the controller gathered Morrison's recorded data. A classification officer followed, reminding him in blunt terms that any discussion to test outside authorized channels would lead directly to a court-martial. Morrison signed the required paperwork and watched as the magnetic tapes were sealed inside a locked courier pouch and carried away. He had spent 5 years monitoring aircraft across European airspace. Radar theory was not abstract to him. It was practical knowledge. He understood radar cross-sections, signal behavior, and the physical limits governing how radio waves reflected from metal structures. What he had just tracked ignored all of it. The technical report Morrison submitted under special classification listed the aircraft's designation, a deliberately vague reference to Project Blue, and included raw datasets showing radar returns that shifted across 4 orders of magnitude. His conclusion, written in the restrained, clinical language expected of military documentation, stated only that the test aircraft displayed radar behavior inconsistent with established aircraft design principles. It was the safest way to describe an experience that felt like tracking an object that could not decide whether it existed. 3 weeks after the Minsk radar anomaly, a consolidated intelligence report arrived on the desk of Colonel Viktor Balino in Moscow. Balino had spent 12 years with the GRU analyzing Western aviation developments. He had studied every major American fighter program, from the F-4 Phantom to the newly deployed F-15 Eagle. Radar cross-section modeling, material science, and aerodynamic trade-offs were all familiar territory. The data from Baranov Station prompted him to reach immediately for a classified line. Within 48 hours, Balino convened a panel of experts at the Central Aerohydrodynamic Institute outside Moscow. The group reviewed the radar recordings, the full technical specifications of the P-18 tracking system, and the meteorological conditions from the night of the incident. Professor Dmitry Volkov, the Soviet Union's foremost authority on radar signature reduction, examined material for 6 uninterrupted hours before delivering his verdict. The fluctuations were genuine. The radar equipment had operated correctly, and nothing within the known framework of Soviet aviation physics could account for the observations. Volkov summarized the established techniques for reducing radar visibility. Radar-absorbing materials could lower returns, but only modestly, perhaps by 50% under ideal conditions. Nothing they knew could do this. Nothing close to the 1,000-fold reduction reflected in the data could be explained by known techniques. Careful shaping of airframes, angling surfaces, and refining curves could redirect radar energy away from the transmitting antenna. This was how the American State Route 71 achieved a radar signature far smaller than its physical dimensions would suggest. But such methods produced stable, predictable results. What the American aircraft demonstrated was something else entirely. Its radar presence behaved like a switch, on one moment, absent the next. Volkov initially suggested an advanced form of active electronic countermeasure. Perhaps the aircraft carried a jamming system capable of canceling its own reflected radar energy before it returned to the receiver. The idea collapsed under one critical observation. Radar operators had detected the effects simultaneously across multiple frequencies. No electronic jammer could anticipate and neutralize every wavelength in real time. The inquiry widened. KGB technical specialists questioned NATO defectors and combed through Western aerospace publications searching for any hint of a revolutionary advance. They found none. American companies openly published research describing gradual improvements, slightly better radar-absorbing coatings, marginal refinements to airframe geometry. Nothing radical. Issues of Aviation Week in Space Technology displayed familiar aircraft layouts, swept wings, rounded fuselages, conventional control surfaces. There was nothing that could account for an aircraft that vanished from radar at will. Balino requested full access to the Soviet Union's own low observability research. The classified files revealed only limited programs, largely focused on applying radar-absorbing materials to submarines and missiles. Aircraft studies have been explored and then quietly set aside. The obstacle was fundamental aircraft required wings to generate lift, engines to create thrust, and a fuselage to house fuel, avionics, and weapons. These were large metallic structures designed to interact with airflow, and by their nature, they reflected radar energy. Soviet aerodynamic models had long shown that pushing a fighter's radar cross-section below 1 square meter would demand such severe compromises in speed, maneuverability, and payload that the aircraft would be militarily worthless. Yet the Americans appear to have achieved roughly 0.1 square meters, while retaining full jet performance that by December 1977, Balino's team reached. An uneasy verdict. The United States had crossed a threshold in applied physics that Soviet science could neither replicate nor fully explain. The classified report forwarded to the Ministry of Defense cautiously acknowledged several theoretical possibilities, but offered no definitive answer. Perhaps the Americans had uncovered a new class of materials with unusual electromagnetic behavior. Perhaps they had developed computational techniques capable of predicting radar interactions with unprecedented accuracy. Or perhaps they had reimagined aircraft design itself, reshaping entire airframes around principles Soviet engineers had never explored. The report's closing recommendation was clear: immediate investment in counter-stealth radar systems and intensified intelligence efforts targeting U.S. aerospace research facilities. What the document did not acknowledge, because Balino had no way of knowing, was that the theoretical basis for America's apparent breakthrough already existed in Moscow. It sat quietly on library shelves, published in Russian, authored by a Soviet scientist, and overlooked for 15 years. The decisive insight emerged from an unexpected direction in March 1978. A CIA technical intelligence analyst, Dr. Kenneth Perko, was conducting routine reviews of translated Soviet scientific journals, part of the agency's ongoing monitoring of Eastern Bloc research. Most of the material was familiar and incremental: wind tunnel experiments, propulsion efficiency studies, metallurgical refinements. One reference nearly escaped his notice. Buried in a footnote of a Ukrainian aviation journal was a citation to a 1962 paper by Pyotr Ufimtsev titled Method of Edge Waves and the Physical Theory of Diffraction, published by the Soviet Radio Publishing House in Moscow. Perko requested the complete text through the CIA's Technical Document Acquisition Program. When the translation arrived 6 weeks later, he read it once, then read it again before reaching for a secure phone line to Langley. The paper laid out a rigorous mathematical framework describing how electromagnetic waves diffract around sharp edges and complex geometries. Ufimtsev had solved equations capable of predicting radar reflections with a level of precision both Soviet and American engineers had previously assumed to be computationally impractical. The mathematics was formidable, dense with special functions and boundary condition analysis, but its consequences were unmistakable if the exact geometry of an object's edges was known. Its radar signature could be calculated with extraordinary accuracy, and if it could be calculated, it could be designed more. Critically, the process could be reversed. Instead of shaping an aircraft and hoping for a low radar return, designers could begin by defining the desired radar signature. The edges came first. Once the acceptable level of reflection was calculated, an aircraft could be constructed around those parameters. Perko forwarded the paper to the Defense Advanced Research Projects Agency marked as high priority. Within days, Dr. Alan Faust, DARPA's chief scientist for advanced propulsion, was studying Ufimtsev's equations alongside engineers from Lockheed's Advanced Development Project Division, better known as the Skunk Works. They immediately understood its significance. Until then, American engineers had relied largely on intuition and repeated testing to reduce radar cross-sections. They would alter a curve, measure reflection, adjust the shape, and test again. The approach was costly, time-consuming, and constrained by educated guesswork about how electromagnetic waves interacted with complex surfaces. Ufimtsev's work removed the uncertainty entirely. His mathematics provided a complete physical description of radar behavior. As Faust dug deeper into Ufimtsev's history, the irony became unmistakable. Pyotr Yakovlevich Ufimtsev had published the research in 1962 at the Moscow Institute of Radio Engineering. The Soviet Academy of Sciences had reviewed the paper, praised its mathematical rigor, and archived it as an elegant theoretical contribution with no obvious practical use. Soviet aircraft designers never applied it. The equations were formidable, requiring enormous computational effort even for relatively simple geometries. In 1962, the Soviet Union simply did not possess computers powerful enough to apply Ufimtsev's method to something as complex as an aircraft. So the work remained on library shelves, occasionally cited in academic discussions of electromagnetic theory, but ignored by engineers building real machines. American engineers had the missing piece. By 1975, Lockheed Skunk Works had access to CDC's 7,600 supercomputers capable of executing billions of calculations per hour. When Ufimtsev's equations were paired with that computational power, the previously unthinkable became practical. Designers could represent an aircraft as a collection of flat facets and sharp edges. Using mathematics, they could calculate how radar energy reflected from each edge, and then adjust those angles until the reflection scattered harmlessly away from hostile radar receivers. With sufficient computing power, the machine could evaluate thousands of design variations in a matter of hours, work that would have required human engineers decades using conventional trial-and-error techniques. The CIA's technical assessment, finalized in May 1978, reached a stark conclusion. The United States had achieved stealth capability by applying Soviet mathematical theory that the USSR itself had published and then neglected. The report emphasized an uncomfortable detail. Ufimtsev's original paper remained accessible in Soviet technical libraries, untranslated into English until American intelligence obtained it, and seemingly unread by Soviet aircraft designers who might have used it to replicate the same capability. The Americans had gained a decisive advantage by completing an assignment the Soviets had set for themselves and then forgotten. Ufimtsev's equations addressed a problem that had frustrated physicists for generations. When radar energy strikes an aircraft, it does not reflect cleanly like light from a polished mirror. Electromagnetic waves interact with every contour, edge, and break in the surface. They bend around corners, scatter from protruding structures, and form intricate interference patterns. Earlier attempts to model these interactions depended on mathematical approximations that worked for simple geometries, spheres, cylinders, flat plates, but collapsed when applied to the complex shape of an aircraft. The dominant approach, known as a physical optics approximation, treated radar reflections as if they were light rays bouncing off curved mirrors. That method worked reasonably well for smooth surfaces whose curvature was large compared to the radar wavelength. Aircraft were nothing like that. Wings met fuselages at sharp angles. Engine intakes formed deep cavities. Tail surfaces intersected at precise, abrupt junctions. At these edges and discontinuities, physical optics failed. The approximations missed critical effects: how waves wrapped around sharp corners, how energy concentrated at intersection points, and how secondary reflections bounced between nearby surfaces. Ufimtsev attacked the problem from a different angle. Rather than treating the aircraft as a single smooth body, he focused on the edges themselves. His method of edge waves analyzed each geometric discontinuity as an independent source of diffraction, the very features traditional models could not handle. Every sharp corner, every junction between surfaces, and every sudden change in geometry became, in Ufimtsev's framework, a source of diffracted radiation. When a radar wave encountered an edge, it did not merely bounce away. Instead, it generated a secondary wave that traveled along the edge itself, forming what Ufimtsev described as edge currents. These currents then emitted their own electromagnetic fields, governed by precise and predictable mathematical laws. The brilliance lay in the mathematics. Ufimtsev derived integral equations that defined exactly how these edge-generated waves behaved. For a straight edge, the solutions involved Fresnel integrals and modified Bessel functions. For curved edges, the problem grew more involved, requiring path integrals that follow the geometry of the edge. The complexity was formidable, but not unsolvable. The equations were exact, deterministic, and fully solvable with adequate computational resources. Provide the geometry of an edge, its length, curvature, orientation, and angle relative to the incoming radar wave, and Ufimtsev's formulas would yield the precise strength and direction of the diffracted electromagnetic field. The practical consequences transformed aircraft design. Traditionally, engineers optimized an aircraft for aerodynamics first, then measured its radar cross-section in costly test ranges, hoping for incremental improvements. Ufimtsev's approach inverted that logic. Designers could begin by specifying the radar signature they wanted. Using the edge-wave equations, they could compute the exact geometric configuration needed to achieve it, and only then design the aircraft around those constraints. The computer replaced the test range. Each design iteration could be evaluated mathematically before a single piece of metal was cut. The equations also revealed a deeply counterintuitive result. Smooth, continuous curves, long assumed to gently disperse radar energy, often produce complex and unpredictable reflection patterns, because every point along the curve contributed differently to the overall return by contrast, sharp edges and flat panels, features that appeared obviously radar visible, could be arranged to direct energy with extraordinary precision. When flat surfaces were positioned at carefully calculated angles, the edge-generated waves interfered destructively, canceling one another out. The net radar return could be reduced to nearly zero. All of this had been laid out in Ufimtsev's 1962 publication, complete with rigorous derivations, worked examples for idealized shapes, and clear explanations linking the mathematics directly to physical electromagnetic behavior. Soviet engineers had read the paper, admired its theoretical sophistication, and then archived it. The equations demanded far too much computation to be useful without digital machines capable of processing thousands of edge integrals at once. By the time the Soviet Union possessed sufficient computing power in the early 1970s, Ufimtsev's work had faded from memory, remembered, if at all, as an obscure academic contribution to diffraction theory rather than as the blueprint for radar-invisible aircraft. In California, the moment of realization came abruptly. Ben Rich stared at the computer printout and felt the sense of impossibility begin to dissolve. It was April 1975. As deputy director of Lockheed Skunk Works, Rich had spent nearly 2 years watching his teams wrestle with a daunting challenge in the Defense Advanced Research Projects Agency. DARPA wanted an aircraft with radar cross-section just 1% of that of conventional fighters. Every proposal from the aerodynamicists, sleek curves, smooth blending, carefully refined contours, had failed. Radar modeling showed only marginal improvements over existing aircraft. Rich had started to believe the requirement violated the limits of physics. Then Dennis Overholser, a young mathematician in the Skunk Works radar analysis group, walked into Rich's office carrying a translated Soviet paper and an idea that defied decades of aircraft design philosophy. Forget curves. Build the aircraft entirely from flat surfaces, arrange at exact angles calculated using Ufimtsev's edge-wave equations. Overholser had already written computer code that implemented the Soviet physicist's mathematics. He fed in geometric descriptions of faceted, flat panel shapes and let the program compute their radar returns. The results were astonishing. A diamond-like configuration composed of flat panels, oriented to deflect radar energy away from the transmitter, produced calculated radar cross-sections below 0.01 square meters, nearly 1,000 times smaller than DARPA's requirement. Rich immediately convened his top engineers inside the secure Skunk Works facility in Burbank. Dick Scherer took responsibility for aerodynamics. Bill Schroeder oversaw flight control systems. Overholser was placed in charge of radar signature design. The development process was reversed from every aircraft program that had come before it. Traditionally, engineers shaped aircraft for optimal aerodynamic performance first. Radar specialists then attempted to reduce visibility through coatings and minor geometric tweaks. In this case, Overholser defined the aircraft shape for radar invisibility from the outset, and everything else would have to adapt to that decision. Once Overholser defined the shape, the burden shifted to the aerodynamicists. They had to make it fly, using a CDC 7600 mainframe accessed remotely through telephone lines. Overholser ran computations on thousands of possible flat panel arrangements. He broke the aircraft into triangular and quadrilateral facets, perfectly flat surfaces with straight edges that the mathematics could model exactly. Each facet was oriented to redirect radar energy away from anticipated threat directions. The geometry was dictated entirely by electromagnetic calculations, not by aerodynamic tradition. The nose panels were angled downward at 72.5 degrees from horizontal. The leading edges of the wings were swept back at 67.5 degrees. Every alignment traced back to a radar equation. After 6 weeks of continuous computation, Overholser produced a final configuration. It barely resembled a conventional airplane. The design looked almost childlike, a diamond-shaped form built from flat triangular panels, sharply swept wings, and a faceted fuselage. There were no smooth curves, only edges, angles, and planar surfaces arranged exactly as Ufimtsev's theory predicted radar energy would behave. Dick Scherer reviewed the aerodynamic analysis and delivered grim conclusions. The faceted structure was aerodynamically awful. Flat panels produced lift inefficiently. Sharp edges generated excessive drag and turbulent vortices. The aircraft would be unstable in all 3 axes, pitch, roll, and yaw. No human pilot could fly it unaided. Ben Rich made the decision without hesitation. Install fly-by-wire flight control systems. Electronic computers would artificially stabilize the aircraft, making thousands of tiny control adjustments every second to keep the inherently unstable platform under control. The technology was already available. The F-16 program was proving early fly-by-wire concepts workable. With sufficiently advanced software, pilots would never realize they were flying an aircraft that naturally wanted to fall out of the sky. Lockheed submitted the design to DARPA in July 1975. The proposal included Overholser's radar modeling, predicting radar cross-sections as low as 0.003 square meters, roughly 1,000 at conventional fighter aircraft. DARPA's evaluation board examined the mathematics, validated the computational approach, and accepted the results. They awarded Lockheed the contract. The contract was awarded to construct 2 experimental flying prototypes. The program was given the code name Blue, and work began in November 1975 at a highly classified Lockheed facility in Burbank. Every component was manufactured to tolerances measured in thousandths of an inch, ensuring that each flat surface matched Ufimtsev's mathematical predictions exactly. The first Blue prototype eventually stood on the ramp at Groom Lake, Nevada, bearing no resemblance to any conventional aircraft. In the early hours before sunrise on November 16, 1977, test pilot Bill Parks slowly circled the aircraft. inspecting its sharply angled panels as floodlights bounced off the faceted surfaces in stark geometric reflections. The aircraft was 47 feet long with a wingspan of just 22 feet, about the size of a small business jet, but weighed only 12,000 pounds due to its lightweight composite skin stretched over skeletal frame. Park, a Lockheed test pilot since 1960, had flown many experimental designs, yet nothing compared to the strange, angular machine. The maiden flight lasted just 20 minutes. Taking off from the dry lake bed, Park climbed to 10,000 feet and conducted basic handling tests while chase aircraft observed from a safe distance. The fly-by-wire control system functioned as intended, constantly correcting the aircraft's naturally unstable configuration. After landing, Park briefed the engineers and confirmed that the aircraft was controllable, though challenging to fly. The true challenge, however, lay ahead. The radar cross-section evaluation scheduled for December. Preparing the test range took 3 weeks. Engineers deployed radar transmitters around Groom Lake at ranges from 5 to 40 kilometers, tuned to frequencies used by Soviet early warning, acquisition, and fire control radars. Each radar system was carefully calibrated using metal spheres of known size, which produced precisely predictable radar returns. The testing procedure was exacting. Park would fly straight, level passes at specified speeds and altitudes, while ground stations recorded the reflected signals. The results would determine whether Ufimtsev's theoretical calculations held true in the real world, or whether the mathematics would fail when confronted with physical reality. December 1st, 1977, Park took off at 0600 hours and turned toward the first radar measurement corridor. On the ground, radar operator Thomas Reed stared at his display as a blue approached. At a distance of 20 kilometers, the aircraft should have appeared as a strong, unmistakable contact. Instead, Reed's screen remained blank. He double-checked his systems. Everything was functioning correctly, and the chase aircraft showed up clearly. Half Blue, however, was still invisible. Only when the aircraft closed to 10 kilometers did Reed finally observe a faint return. The measured radar cross-section was just 0.025 square meters. An F-4 Phantom at the same distance would have produced a return of roughly 6 square meters, making Half Blue about 2,400 times harder to detect. Testing continued throughout December and into January. Park flew repeated passes, presenting the aircraft at every possible angle and attitude, while ground-based radars recorded the reflections. Head-on approaches yielded radar cross-sections as low as 0.02 square meters. From the side, normally the most radar-visible orientation for traditional aircraft, the return measured only 0.04 square meters. Even in the worst-case scenario, with radar looking directly up at the flat underside, the signature never exceeded 0.08 square meters. The results matched Overholser's computer models precisely. Ufimtsev's equations had proven accurate in real-world conditions. By carefully positioning flat surfaces at calculated angles, Lockheed had built an aircraft that redirected radar energy away from transmitters with remarkable effectiveness. The consequences were immediate and profound. Soviet air defense doctrine depended on early warning radars detecting hostile aircraft at distances of up to 200 kilometers, allowing time to launch interceptors and activate missile systems. Half Blue's tiny radar signature meant detection would occur only at around 20 kilometers, less than 2 minutes of flight time at typical attack speeds. By the moment defenders realized an aircraft was inbound, it would already be over the target. An air defense network that had cost billions, thousands of radar installations, surface-to-air missile sites, and interceptor squadrons had effectively been neutralized by geometry and mathematics alone. A technical assessment delivered to the Pentagon in February 1978 concluded that Half Blue achieved radar cross-sections 1/10,000th that a conventional fighter aircraft. The program conclusively demonstrated that stealth technology was not just theoretical, but operationally viable. In response, the U.S. Air Force immediately approved development of a combat-ready stealth aircraft based on Half Blue's design philosophy. The new program was designated the F-117 Nighthawk. The full-scale production was scheduled to begin in 1980, resulting in a new generation of aircraft effectively invisible to Soviet radar, ironically built on mathematical principles published years earlier by a Soviet physicist and then largely disregarded at home. When reality began to sink in, the Soviet reaction moved rapidly from disbelief to alarm, and finally to hurried, improvised countermeasures. By mid-1978, KGB technical intelligence had pieced together enough scattered information to grasp what the United States had accomplished. Reconnaissance satellites captured images of Lockheed's Burbank facility, revealing unfamiliar aircraft under construction, sharp-edged, faceted shapes that bore no resemblance to traditional airframes. Intercepted communication from U.S. Air Force test ranges referred to radar cross-section values reduced to fractions of a square meter, confirming that something extraordinary was underway. Soviet aerospace specialists reviewed the accumulating evidence and reached an unsettling conclusion. American engineers had achieved radar invisibility not through advanced electronic warfare or exotic materials, but through basic geometric design concepts that Soviet research had failed to apply. In August 1978, the Sukhoi Design Bureau received emergency funding to explore stealth modifications for aircraft already in development. Chief designer Mikhail Semenov gathered his top aerodynamicists and radar experts and issued a clear directive: reduce the radar cross-section of the Su-27 fighter to levels comparable to the American breakthrough. After 6 months of intensive analysis, the team delivered its verdict. This goal was unattainable. The Su-27's configuration was already fixed. Its swept wings, smoothly curved fuselage, and large vertical stabilizers were optimized for aerodynamic efficiency. Altering them enough to achieve stealth will require a complete redesign of the aircraft. Radar-absorbing coatings, the engineers concluded, might cut the signature by half at best. American stealth aircraft, by contrast, achieved reductions by factors of thousands. The technological gap could not be closed through gradual upgrades or add-on solutions. The McCoy Design Bureau chose a different path. Rather than attempting to adapt existing aircraft, it began preliminary work on an entirely new stealth fighter concept, one built from the outset around sharp angles, flat panels, and faceted geometry designed to minimize radar detection. The engineering teams quickly ran into serious obstacles. They understood the objective clearly: use flat, angled surfaces to deflect radar energy away from hostile emitters. What they lacked was the mathematical foundation needed to determine the most effective shapes and orientations. Without access to Ufimtsev's edge-wave equations, their work became a process of trial and error. Engineers built faceted scale models, tested them in radar measurement facilities, adjusted the panel angles, and then tested again. The cycle was slow, costly, and yielded only modest improvements. By 1982, the most advanced stealth prototype produced by the McCoy Bureau still had a radar cross-section of roughly 0.5 square meters, about 50 times larger than its American counterparts. At the same time, the Soviet military research community shifted focus toward developing counterstealth technologies. If Soviet aircraft could not equal American invisibility, perhaps Soviet radar systems could be adapted to find stealth aircraft anyway. Phasitron, the USSR's premier radar design organization, examined several potential solutions. One promising avenue involved using lower-frequency radar operating at longer wavelengths, which might interact differently with stealth airframes than conventional high-frequency systems. The underlying physics was valid. Ufimtsev's edge-wave effects weakened at longer wavelengths. However, lower frequencies required much larger antennas and delivered far poorer target resolution. A radar capable of detecting a stealth aircraft at extended range might still be unable to provide the precision needed to guide missiles for an intercept. Another option emerged from the use of static radar architectures. Traditional radar systems transmit and receive from the same location. In contrast, bistatic radars separate the transmitter and receiver, increasing the chance of capturing energy that a stealth aircraft deflects away from the emitter. Soviet engineers constructed experimental bistatic radar networks around Moscow and other critical military sites. These systems showed promise, detecting low observable test aircraft more reliably than conventional radars. However, bistatic networks were inherently stationary and require extensive infrastructure, multiple synchronized transmitters, and receivers with overlapping coverage zones. Expanding such systems across the vast territory of the Soviet Union would demand enormous investment, cost billions of rubles, and take many years to complete. By 1985, Soviet defense planners were forced to confront a bleak reality. The United States had secured a decisive technological lead in aircraft design. Closing that gap would require either uncovering the mathematical foundations behind American stealth, principles Soviet intelligence believed originated in publicly available Soviet research, or committing vast resources to counter-stealth systems whose effectiveness remained uncertain. At the same time, production of the American F-117 continued at pace. Intelligence assessments indicated that by 1990 the United States would field between 50 and 60 operational stealth fighters. The Soviet air defense network, built at enormous cost over 4 decades, now faced irrelevance against an adversary that had achieved invisibility using equations first published in Moscow. Pyotr Ufimtsev discovered his unexpected role in American stealth development in a familiar Soviet manner, through carefully phrased inquiries from KGB officials. In 1985, Ufimtsev, by then retired from the Moscow Institute of Radio Engineering, was visited by 2 men in dark suits who wanted to revisit his 1962 paper on edge-wave diffraction. They presented satellite images of sharply angled American aircraft and asked whether his mathematics could predict the radar signatures of such designs. After studying the photographs, Ufimtsev confirmed what the officers already suspected. Yes, his methods could accurately calculate the radar reflections of faceted, angular shapes. That capability was precisely what he had described more than 2 decades earlier. When asked why Soviet aircraft designers had never applied his work, Ufimtsev explained calmly that in 1962 the Soviet Union lacked the computational power needed to apply his equations to complex 3-dimensional structures. He had published the work as a theoretical contribution to electromagnetic diffraction, not as a practical design guide. By the time Soviet computing technology advanced in the 1970s, his paper had faded into obscurity, archived in technical libraries as interesting but impractical academic research. The Americans, it seemed, had rediscovered it, recognized its potential, and built an entire weapons program around mathematics that Soviet engineers had overlooked. The irony was unmistakable. At a Ministry of Defense technical review in 1986, Marshal Sergei Akramov summarized the situation with rare candor. The United States, he noted, had gained a strategic advantage simply by reading Soviet scientific literature more carefully than Soviet specialists themselves. Ufimtsev's paper had never been classified. It had always been openly available. American analysts had merely done better analysis. Identifying real-world applications that Soviet institutions had failed to pursue. As a result, the Soviet Union now faced aircraft it could not reliably detect, using radar systems that had consumed enormous portions of the defense budget for decades. The real-world impact became undeniable during the 1991 Gulf War. American F-117 stealth fighters carried out nearly 1,300 combat missions deep inside Iraqi airspace, protected by Soviet-built radar and missile systems. These defenses include the same SA-2, SA-3, and SA-6 surface-to-air missiles deployed around Moscow and major Soviet military installations. Iraqi air defense units, trained by Soviet advisors and operating according to Soviet doctrine, never succeeded in engaging a single stealth aircraft. While conventional U.S. aircraft encountered intense surface-to-air missile fire, the F-117 struck heavily defended targets in Baghdad without interference. The lesson was unmistakable. Air defense systems designed to detect traditional aircraft were ineffective against an adversary that understood edge-wave diffraction. The mathematical basis of this vulnerability had existed all along, stored in Russian libraries, written in Russian, and published by a Soviet physicist for Soviet engineers. Ufimtsev's edge-wave method had been openly available since 1962. No spying was necessary. No classified secrets were stolen. The Americans simply recognized the importance of open scientific research, translated a paper their opponents had dismissed as impractical theory, and applied it using modern computing power and rigorous engineering. The Soviet failure was not due to a lack of scientific talent or theoretical insight. It was a failure of vision and commitment, a failure to recognize how abstract mathematics could transform warfare when paired with sufficient computational resources. By 1991, As the Soviet Union itself collapsed, Western aerospace journals finally disclosed the full story. Articles in Aviation Week and other technical publications confirmed that the F-117's design relied heavily on Ufimtsev's diffraction theory. The equations that made American aircraft nearly invisible to radar had been developed in Moscow, reviewed by Soviet scientists, and then set aside as academically interesting but practically useless. In the end, the United States prevailed by studying Soviet science more carefully than the Soviets did themselves, turning theoretical physics into operational technology, and using discarded mathematics to undermine an empire struggling to defend itself against invisibility of its own making.